All right, let's get started. Okay, so let's briefly review what we covered in the last lecture. So basically, in the last lecture, we finished talking about the AM demodulation. So remember that AM signal is nothing but the DSBSC and plus the carrier, right? And then we talk about the bandwidth efficient amplitude modulation. Because for the DSB signal, so we kind of double the bandwidth, right? For the baseband signal, the modulated signal has like twice of the bandwidth of the baseband signal, right? So that may not be good. And because of the symmetry of the signal, then half of the bandwidth might be wasted, right? So then I want to figure out a way to transmit only half of the bandwidth. So it's called SSB, single sideband modulation. Okay, here are the details for the AM demodulation. So firstly, we cover square demodulator, right? So this was covered in 2 lectures ago, right? So we don't mention too much here. So this is what we covered in the last lecture. So basically, what we have here is called the rectifier diode amplitude envelope demodulator. So basically, what we do here is that so basically we so this is a receiver structure, right? The demodulator. So basically, we pass the received signal SAM through a diode, right? So basically, it's also called rectifier or half-wave rectifier, right? And after that, we pass that through a LPF then. So, and then we can get rid of the AC component to get the output signal, right? So this is a kind of a little bit more complicated circuit structure, right, in the book. So also, if you continue looking at the book, so there's another structure that can be much easier. So which basically means that we replace the whole this part, by only a resistor and a capacitor, right? So this is an easier envelope detector. Meanwhile, it's also a low-pass filter. Okay, so you can take a look on how we can apply the property of the capacitor to get our original signal out, right? But the disadvantage of that is there's some imperfection in the received signal. Okay, but we didn't cover much of that in class. So one thing we want to emphasize here a little bit that I think I forgot to mention is that the only point we use this kind of structure is that it's non-coherent. So basically, it means that we do not need to generate a local carrier, right, which may have a different phase compared to the transmitted signal. Okay, yeah, that's the main reason we use this kind of demodulator. Okay. And then, so we cover SSB. So basically, as what we mentioned before, so here, the reason we want to introduce it is because that for the modulated signal, we have 2B for the bandwidth, right? So here, we denote this half as the USB, right? So this and that is the upper side band. And so what is inside this part and this part is the lower side band, okay? And so the idea is only to transmit half of the band to for the transmission, right? And so here's some terminology here. So if we send a USB, it's called USB modulation. If we send LSB, it's called LSB modulation. Okay, and here's a figure to summarize it, right? So basically, so this is our DSB signal, right? And this is the upper side modulation. So this is a lower side modulation, right? So yeah, so yeah, maybe I want to emphasize one more thing here. So basically, you can see it may not be that easy to do, right? The reason is that, so for the original signal, we want to move this to here and this to here, right? So if we use USB, right? And this is kind of a weird operation, right? How to move half of it to one side and the other half to the other side, right? So this is kind of where the difficulty comes from. That makes sense, right? Because if we times a cosine or if we times a complex exponential, it will move the whole thing, right? It cannot separate it, right? So we need to deal with that, right? That is the basic idea, right? So basically, yeah, in the lecture notes, we talk about how we're gonna do that, right? So basically, do you remember how we do that? Right, how we separate the signal by half. Yeah. Yeah, unit step signal, right? So we multiply a unit step signal in the frequency domain, right? Not in time. I think this is the first time we do that in the frequency domain, right? So in the frequency domain, then we can separate the original signal by half, right? So if we use f, then it's this half, and if we use a u minus f, we can get this half, right? So which is very good. And in terms of the implementation, so we don't want to use u of f, right? Because the inverse Fourier transform involves a delta signal because we have a kind of the DC component in the frequency domain, right? So we shift it a little bit to make it as 1 plus a sine signal, right? To get rid of DC signal, so that will be easier for our implementation, okay? Yeah, that is basically the idea. So, okay, and as we recall, so in the frequency domain, it's a multiplication between the signal, original signal, and a sine signal, right? So in the time domain, it will be a convolution, right? So this is a convolution described in the time domain. So we use our original signal convolutes with 1 over pi t. So this is basically the Fourier transform of the sine signal, right? So if we do this if we do this convolution, it's called Hilbert transform, okay? So we have a special name for it. Technically, it's not really a transform, right? Because it's a convolution, right? But conventionally, we call this Hilbert transform, right? That is very important. Yeah, I think. Yeah. So here are some properties of the Hilbert transform. So if we do, so this is a Hilbert transform, right? And when we use it, we need to multiply j in front of it, right? And when f is bigger than 0, we can see that that's equal to minus j. When f is less than 0, it equals to j, right? And then because it's j, then we can write that as a phase, right? So basically it means that when f is bigger than 0, so we move the signal by phase minus pi over 2. And if f is less than 0, we move the phase to the positive side of pi over 2, right? So that's basically what is described here. So the magnitude is just 1, so we don't change anything for the signal in terms of the magnitude. But for the phase, we do a phase shift by either pi half or minus pi half in the frequency domain, right? That makes sense? Yeah, if you think it twice, it sort of makes sense, right? Just cancel the other side, right? So basically, yeah, that is what we're doing here. All right, let's see. Yeah, let's see what we're going to cover today. Today is our lecture 16. It's 16, right? Should be 16. Okay, and the first topic, again, we will talk about the bandwidth, efficient, amplitude modulation. Okay, and here, as we said, we have 3 things to cover. The first one is SSB, right? Single side band modulation. And second is called VSB, vertical side band modulation. And last one is called QAM, QAM. So it's called quadrature amplitude modulation, right? So yeah, hopefully we can finish talking about today, and then we'll talk a little bit on the applications. of amplitude modulation. Okay, and so in the next lecture or in the future, just give you a brief look ahead. So after this, we're going to cover angle modulation. Okay, for angle modulation, so we're going to talk about the frequency modulation, FM, and phase modulation, PM. Okay, and that will be the last topic for the analog communication part. Okay, yeah. So, but I don't think we can talk about this today. Okay, so let's focus on the first one and see if we have time to talk about the second one. Okay, so yeah, let's do a very brief recall of the last time. Right. So basically, what we're going to do is as follows. So basically, we're going to let's give some notation here. Let's say this is our original signal. Okay, so make it a little bit easier to draw. So this is our MF. Okay, so in order to make our SSB modulation, so basically we're going to move this part to here and then move this part to the other side, right? And here is our carrier frequency, FC and minus FC. Right, so this is our SSB modulated signal. Okay, so to give you a name to make our life a little bit better, so we call this guy, oh, not this guy, we call this guy, so this half as M plus F. Right, M plus F is basically this side, right? And then we call this side M minus F, right? Because we have to treat them separately, right? Okay, so this is basically how we denote that. And in the last lecture, we focused on this side, right? The right-hand side. So basically, we can see that M plus F, so that's equals to MF multiply what? A unit step signal, right? So unit step signal, as we said, we write that as 1 plus sine of F. Okay, remember sine of F is defined in this way. So this is 1 if F is bigger than 0, if it's minus 1, if F is less than 0, right? In the middle, it will be just 0, okay? In the book, somehow it was written this way, but if you want, right, it will be 0 when F is 0, okay? Yeah, because for Fourier transform, a single point really doesn't matter. And later, we want the signal to be odd signal, so F0 has to be 0. Okay, so this is how we treat it. And we miss a half, right? Right, because we shift this guy above, right? We need to divide it by 2. Okay, very good. Okay, and with that said, so basically now we can see that. So by using the Hilbert transform in the time domain, so this is what we do, right? So in the time domain, so it is nothing but for the M of F, so it's not changed, it's empty, right? But the other side is that, so it is empty, convolutes 1 over pi t, so we have to multiply j here. Okay, because the Hilbert transform of this guy, there's a j there, right, if you remember. Okay, so we need to multiply j there. Okay, and and then let's see. So this is basically the plus part, right? So let's denote this, as in the slide, let's denote this as sh of t. So h basically means the Hilbert transform. Okay, so this is the plus side. And how about the minus side? So what is the minus side? Yeah, can I take a guess? So basically, the only difference here is that we need to multiply this by u, u of minus f. So if it's u minus f, it'll be nothing, but we put a minus f here, right? If we put a minus f here, there will be a minus t here. Minus t here, right? If there's minus t here, then we just need to minus that. It'll work. Okay, so basically, if it's on the other side, so what we do is like this. It's a 1 minus the sign. Right, so this is basically what is happening. Okay, and we can write one more step here. So basically, you will use that times that. So basically, that will be the Hilbert transform, right? So we can write that as basically this guy, right? And similarly, yeah, there will be a 2 here. And similarly, we can write this as mf over 2 plus j capital MHF over 2. Right. Yeah, that's how we represent it. Any questions? Okay, so now we know how to represent the plus part and the minus part, right? Okay, so given this, so how can we write down the modulated signal, right? What is our modulated signal as USB of f? Look at. Right, in the frequency domain, it's easy to write, right? In the time domain, it may not be easy, but in the frequency domain, it is easier, right? So basically, we just need to move this guy to this part, move this guy to the other part, right? How to move this guy to this part? I mean, the frequency domain, yeah, just minus FC, right? That makes sense? So basically, this equals to nothing but m plus f minus fc, and then we need to add m minus f plus fc, right? So this is basically what the signal look like in the frequency domain, right? Questions? Okay, great. So now let's do some manipulation to see what this signal look like exactly, right? So basically, for the first part, so we need to copy this, right? Because m plus equal to this guy, right? So basically, for the first part, what we have is that we have half. So it is f minus fc plus j times mh f minus fc, right? That's the first term. And for the second term, it is m f minus fc minus j mh f plus fc, right? I have 4 terms here. So now let's do some manipulation. Yeah, we are already here. So basically, yeah, I can write it here. So for the manipulation, we can combine these two and these two, right, and see what we can. Wait, here should be plus. Oh my God, this is minus. Sorry. Yeah, we can combine these two and see what we get, right? So for the first and third term, so basically what we have is this. right? And for these two terms, so basically what we have is this. And J M F plus MH F minus FC minus this term, MH F plus FC. Okay, very good. All right. Okay, so for this guy, does this sound familiar? Does it look familiar? What's that? The what?
The message signal just shifted.
Yeah, so that is what? So we see, yes.
That's the DSB.
Exactly, right? That's a DSB signal, right? So very good. So in other words, so basically we can write this guy in terms of the time domain, right? Because we know this is a DSB modulation. So this is nothing but our original signal m of t multiplied cosine omega ct, right? Very good. So this is basically the first part. And how about the second part? What is that? Right, so if it's not super clear, maybe you can do some manipulation. So we remove this guy, right? We move that to the downstairs. And then we use a minus sign here. Right, if I write it this way, so did you recognize it? Does that look familiar? So what kind of, Fourier transform have this kind of term?
Sine.
Exactly. So that's sine, right? Sine is a cosine, and minus another. Sorry, it's the difference between two complex exponential and divided by 2j, right? So that's basically, therefore, so this basically means that we can use a sine to modulate that to get this term. Okay, yeah, that's basically how we do that in the time domain. Okay. Okay, very good. And then this is basically the modulation part. That make sense? Okay, so in practice, so basically what we do is that we have our original signal multiply a cosine. So basically we have our DSB signal, and then we need to do the Hilbert transform, and then modulate that signal by a sine signal, and then add them together, right? So this is how we do the modulation in practice. Okay. Okay, very good. And given this, so yeah, maybe let me. Yeah, I think here should be plus, right? So now minus. Let me write down how we do the demodulation in a diagram, right? So basically, what we do is as follows: we have our message signal, and then we have two paths. So one path is nothing but a DSB SC modulator. Okay, and then in this way we get our MT cosine omega ct, right? And then, so we have another route. So we need to do a Hilbert transform first. Okay, and after the Hilbert transformation, we get our MH of t, right? And so basically, and then we'll add them together. Oh no, sorry, we need to do a modulation, right? So basically, let me write in this way. So basically, we need a cosine carrier here to come to here to get this signal, right? Okay, and then we need this cosine to this guy and make this multiply that, right? But we cannot do that directly because we have to multiply sine here, right? How can we get a sine from a cosine? Yeah, if we know a cosine, how to get a sine? Yeah, shifted by pi over 2, right? So we shift it to the right by minus pi over 2, and then we have a sine, right? If we have a sine, then how can we mix this and that, right? It will be the same procedure as this, right? So in practice, so this is a circuit. We can do it, right? So we can basically use the exact same circuit, right? So basically, here we're passing that through a what? A DSP SC modulator, right? And then here we can get our this signal, okay? And then after that, we just add them together. Right? And then, so that's our SSB modulated signal. Okay? Yeah, that's how we do the modulation. That makes sense? Any questions for the modulation part? Okay, so if no question, let's think about demodulation, right? How can we do demodulation for this? Yeah, let's think a little bit. Yeah, how can we do the demodulation? Right, so now let's see how many demodulation approach that we have introduced, right? So the simplest demodulation is for the DSP-SC signal. We just multiply a cosine, right? So that's a coherent demodulation. And then we introduce two approaches for the AM demodulator, okay? And we didn't know anything else, right? So if we didn't know anything else, basically, let's try them, see whether it works or not, right? That's the simplest approach. Right, so basically, we're going to try the simplest one. I mean, conceptually, it's the simplest one. In practice, it may not be, which is the times the cosine. Right, we just times the cosine with it and see what happens. See whether we can demodulate it or not. Right. So basically, so now what we're going to do is as follows. Right. So basically, we have our SSB signal, and then we're going to mix it with a cosine omega CT, right? And see whether we can demodulate it or not, right? Okay, so let's do this. So basically, in this case, E of t. So E of t is denoted by this multiply that, right? So that's equal to S SSB of t cosine omega CT. Okay. And so SSB is nothing. Yeah, I use as USB, right? So yeah, but it doesn't matter. I just make it more general. So just write it USB, LSB. There'll be only a sign difference, so it's not a big deal. Yeah, think about this, right? So if it's LSB, so we just need to multiply U minus F first, and then move that guy to the right instead of left, right? And then vice versa. So there will be a sign difference, but doesn't matter. Okay, so yeah, let's make it more general. So basically, that equals to m of t times cosine omega c of t. Okay, and plus or minus, right? Depends on USB or SSB. MH of t sine omega ct, right? So this is our SSB signal. And then we multiply that with cosine omega ct. Okay? So given that, so let's work it out. So basically, this equals to mt. So we have a cosine here, and we have a cosine here, right? We have a cosine square, right? That is one of our favorite form, right? So we know, we can deal with this part. And then the second part is mh of t sine omega ct and the cosine omega ct. Okay, very good. Right, given this form, what do you think? Can we do the demodulation? Yeah, wait. Yeah, I think I have, yeah, here should be a plus, right? Why is it minus? Plus this, yeah, here should be a plus, right? Yeah, if it's plus, then here has to be a minus, right? Because we have this one has to be in the front for the sign, right? So then here has to be, yeah, minus is correct. Yeah, then, yeah, normally, so this sign means plus or minus. It doesn't matter. Okay, great. Is that right? So just be careful. It's easy to make a mistake here. Right? Questions? Good. Okay, yeah. Anyway, so let's see this form, right? So for the first guy, so we have mt over 2, 1 plus cosine 2 omega ct, right? So that's that's the form that we see all the time. And for the second one, so that is m of h of t over 2. So sine times cosine will equal to half multiplied sine 2 omega ct, right? Okay, so given this form, are we happy? So can we get mt out from this? Yes, we can, right? Just do a low-pass filter. So basically, we can get it, right? Because by doing a low-pass filter, all the high-frequency component, like this, right, that will be gone, right? There are 2 omega c, and then we can get this out. So basically, the coherent filter will work. Okay, so this part, we can remove it by LPF, right? And then our received signal, so basically, we can complete this diagram here. We pass that through LPF, and then get our signal, right? So now we can see our RT is nothing but mt over 2, right? And then we can recover our mt, right? This is how we do the demodulation. Okay, that good? Okay, so but the disadvantage here again, so we need to use a coherent demodulator. So we need to generate a local carrier, right? Which might be challenging. So we're gonna see how we're gonna get it later, but that can be challenging, right? Okay, but the advantage of this this modulation is that we save half of the bandwidth, which is a lot, right? Because the bandwidth is very valuable. Okay, very good. Okay, so now let's see. Besides the demodulation problem, is there any other disadvantage of it? Right, what is that?
The fact that we have to know the phase.
Well, no, that's yeah, exactly. But yeah, that is together with, we need to generate the local carrier, right? So when we do the filtering or when we do the modulation, so which part do you think is the most troublesome? Yeah, so this part is very troublesome, right? So doing this is very complex. And it's very hard to do that in practice. And conceptually, so what is really happening is that let me write it here. So conceptually, what is really happening is that, so we need to get this out, right? Get this part out by u of f. So that's very sharp. Right? It's a sudden change. Right? Sudden change in the frequency domain, it should be hard, right? For example, when you learn this, it's a Butterworth or Chebyshev filter, right? For the transition, you cannot make it super sharp, right? When you implement that in practice, right? So we need a very high order of filter to do that, right? So that's a problem, right? How can we solve the problem? Can we use a lower order filter to solve it? So which means that we don't have this sharp transition. We have a little bit, smoother transition. Will that work? Yeah, that's an idea, right? So basically, in practice, doing Hilbert transform is very difficult, right? So basically, we want something like this. See whether this can work or not, right? So basically, so what we do want is that, we want to do not this sharp transform. So I want to do like, maybe I'll use this green here. So instead of doing this exact sharp transform, so maybe we can do something like this, right? So will that work? Okay, so basically if we do this and the same thing on the other side, so basically, and repeat the same procedure of our SSB, so basically what we're going to get is something like this, right? So after this, it will be like what? How to draw this? Well, yeah, let me see. So this is what we get before, right? So now maybe we can get something like this, right? Then I remove it, right? That makes sense. And then, so here will be our FC, right? Similarly, on the other side, we also get this. Yeah. Maybe something like that. It should be symmetric. Okay. So basically, we have like a little bit additional. Yeah, this is really ugly. A little bit, additional bandwidth. Right? Does that make sense? So can we deal with that? Yeah. So that'll be much easier to be implemented in practice, right? But let's see whether it is possible or not to be implemented, right? So this is our second modulation called VSB. So V means vestigial. Okay. So VSB exactly means this, right? So we cannot get this sharp transition, so we transmit it. So we can only get this smoother transition, okay? And then this is what we transmitted. So do you know the meaning of this word? What does the vestigial mean in English?
Isn't it like something extra that's there that isn't really
Yeah. So let's see what's the meaning in my notes. So yeah, in my notes I said it's a remnant or something left behind. That makes sense, right? So this basically means this part, right? We left a little bit. Okay, so we cannot get the entire thing out, we left a little bit. Okay, and the key reason to use that is we can use lower order filter to get it, okay, in practice. Okay, very good. And so we're not going to go in the details of it. So basically, the design idea is not that different from before. Okay, so I will just write the system diagram, and let's see whether it makes sense or not. So basically, we have our origin signal. So that's very similar to what we can see before. So basically, what we do here is that we multiply this by 2 cosine omega ct, right? Normally, we write a 2 here to compensate the loss of the half. Okay, and then we pass the signal. So know that. So in this case, right, so we're going to pass the signal through some filtering and then to transmit, right? So basically, this is just a filtering operation, right? So before we know exactly what the filtering operation is, but here it's not that clear. Okay, so we just write it as this. So we pass that through a filter called hi of f, right? And then we say we get our VSB signal in the frequency domain. And then, so after some transmission, right? And for the received, this guy, so we'll assume that is the same for now. And then for the demodulation, we're going to do the same thing, right? Multiply that for demodulation. So the idea we're using before completely work, okay? And then we get our signal E of t here. Then we pass through that with an LPF. Okay, so let's see. This is denoted by H naught of f. And then we get our, hopefully we can get our message signal, okay? And this is our transmitter, and this is our receiver. Okay, great. That makes sense. Yeah, sort of. So this is basically the procedure that we do all the time, right? So now, yeah, let's see what does this signal look like, right? So basically, before LPF, let's look at this signal, okay? So basically, so this signal is nothing but. So we're now what we're going to do is that we're going to represent this guy by this guy, okay? See what will happen. So E of t will equals to S VSB. Yeah, I use a different notation here. I use F. Yeah, I think in the book they use phi. Yeah, I copy that from the book. So S VSB t multiply cosine omega ct. Okay, we ignore this 2 here because we always do that. So basically EF. Yeah, let's ignore this 2 here. Will equals to half SVSB F minus FC plus half SVSB F plus FC, right? So this is basically what we do, right? So what it does is that it moves this guy to the right-hand side and to the left-hand side, right? And there will be something in the middle that will overlap, right? So that's how we do the decoding, or to do the demodulation for all the signals, right? So let's see, we pass that through a low-pass filter. So basically, what is going to happen is that it'll be something like this, right? So basically, the signal will be something like this. Yeah, let's assume it's, so So this is exactly equivalent to this, right? Just draw that in a simpler way to illustrate. Okay, so if we move this guy to the left, and move this guy to the right, the higher frequency component will be canceled, right? So after demodulation by multiply a cosine omega c of t. So what will happen is as follows. Right, so this will move to the middle, and this will move to here. Right, and we have something here and something here that can be removed using the low-pass filter. Right, so now let's see. So we have something interesting in the middle here. Right, let's see if because the relation between this and that is we sum them up, right? So let's say if this guy, so here. For this part we don't have any problem, right? But for the middle part where these two overlap, so for the residual or vertiginal part, if that is MF, then we're good. Right? In this case, if it's exactly linear, then so we're gonna have even. Right? That makes sense? Right? I'm not asking so why this can happen. I mean, if this can happen, then we can do the demodulation, right? If we filter this guy out, this kind of thing will exactly be our M of F. Is that right? Yeah, because for this part we're good, this part we're good. Only thing we're not good is the residual part, right? Is the middle part. If the middle part is our M of F, then we're good, right? How to make sure this can happen? So it's to make we need to design this and this very carefully, okay? Yeah, because after this, so we can have something like this, and then after this, so we're gonna do the reverse operation to recover this, right? So this basically means that this filter is somehow the reverse operation of this filter, okay? So for the detail, you can take a look at the book, but this is basically the idea, right? So I want to, when we cannot do the, the sharp filtering, then we have to do something smoother. But after moving the signal in the frequency domain, so sometimes we can get exactly the original signal back by doing this operation. Okay, so we're gonna see this multiple times in this class later, but this is the first time. Okay, so that's basically the idea. Does that make sense? Good. Okay, great. Okay, so. Yeah, lastly, let me very briefly mention about QAM, quadrature amplitude modulation. Okay, so basically, let's recall, so why we need SSB or VSB, right? The point of doing this is to save bandwidth, right? We only need half the bandwidth to transmit the exactly same signal as before, okay? But the disadvantage of it is that it's complex, right? The decoding, the demodulation is very complex. We have to use coherent decoding, demodulation, and for the vestigial amplitude modulation, so we need to design the filter very carefully, right? The demodulation structure is very complex, okay? So is there another way to save the bandwidth? Right, so maybe, yeah, let's recall one thing, and then we stop. So remember that, let's say, for SSB, for this kind of signal, right? Let's recall the structure of it. It's cosine omega ct, and either plus or minus mh, the Hilbert transform of sine 2 pi omega ct. Right, so this is what we are transmitting there. Okay, the point we're using this part is to cancel the negative frequency component of m of t, right? Okay, and then we have single sideband signal. Okay, so in order to save the bandwidth, can we do something else? Right, so basically what we do is that we use half of the bandwidth to transmit the same thing. So equivalently, how about we use the whole bandwidth but transmit 2 messages? Does that make sense? In other words, so we still transmit something like this. Instead of transmitting something, doing something wasted here, so we'll transmit here by a new message, m2 of t. I denote that as m1 of t. Would that work? So now we still have double bandwidth, but we're transmitting 2 messages instead of 1 message. Does that make sense? Okay, and then this is QAM. This is QAM. Okay, so this is the exact idea, very simple, right? So yeah, transmitting, modulation is simple. So we just, multiply a signal with cosine and then plus, another signal with a sine. But the problem is demodulation. So can we demodulate both of them at the same time? Right? Then we're going to discuss that in the next lecture. Okay.